In the last of these three videos, we have discussed the Carnot cycle at length. In these videos, I have explained how a Carnot cycle can be used to describe the set of transitions that take place in a particular special kind of engine. I explained how these engines are driven by the changes in state that happen inside the gases within the pistons inside them. Furthermore, I told you about how the gas inside these pistons was a one-component, one-phase system whose state at equilibrium, in accordance with Gibbs' phase rule, can be characterized using two thermodynamic variables only. Throughout the previous videos, I used the pressure and volume to characterize the state of the gas inside the piston. I thus draw a thermodynamic cycle on the PV plane and explained how the system, on completion of a cycle, returns to the initial thermodynamic state. In terms of the operation of the engine and the set of transitions inside them, I said there were 4 stages. During the first of these stages, the engine is placed in contact with a heat bath and the gas is expanded isothermally, i.e. at constant temperature. During the second stage, the heat bath is removed, the system is thermally lagged, and the gas is expanded adiabatically. During this second stage, the thermal lagging prevents heat from being exchanged with the surroundings, and thus the temperature of the gas drops. In the third step, the system is placed in contact with a heat sink, and the gas is contracted isothermally. The heat sink is then removed, the thermal lagging is placed around the system once more, and the system is compressed adiabatically so that the temperature of the gas increases. I have shown that the Carnot cycle is useful because it allows us to give a precise definition of temperature. We know that heat is absorbed from the heat bath during the isothermal expansion stage of the operation of the engine, and that heat is released to the heat sink during the isothermal contraction stage of the engine's operation. We further know that the amount of heat absorbed and released during these 2 stages is the same for all Carnot engines operating between the same 2 temperatures. As if it were not, we would be able to create thermodynamic cycles which would transfer heat from cold bodies to hot bodies with zero net work expended, which we said was impossible. We thus define temperature using the Kelvin scale shown in the top left of this slide. This tells us that we can calculate the ratio of the temperature of the cold bath to the hot bath by taking the heat output to the cold bath and dividing it by the heat absorbed from the hot bath. In the final video, we then considered the work done during the stages of the operation of the engine in which it is thermally lagged, the adiabatic expansion and contraction stages of the engine's operation. We said during these stages, only the volume of the system changes. All other extensive thermodynamic variables remain fixed. When we thus think about how the state of the system, the values of the extensive thermodynamic variables, change during those parts of the cycle, we find that we are moving about like this. As a consequence, whatever work the universe does on the system acts to change the volume of the system only. We can thus write the following expression for the work done during these adiabatic contraction and expansion stages. In this video and the next, our aim is going to be to arrive at similar expressions for the heat transferred during a transition like the one shown here. That is to say, we want to know how much heat is transferred from the system to the universe if a transition occurs in which the gas does not change its volume. As I alluded to at the end of my last video, the extensive thermodynamic variable entropy is going to be critical in this expression. We will thus begin by looking at how entropy is introduced. The first step in this process involves remembering that the Kelvin scale is defined as follows. This expression can be rearranged as shown here. We now note that Q gives the amount of heat that flows during the transition. We are going to argue that we can calculate this amount of heat that flows during any transitions by integrating over a new extensive thermodynamic variable entropy, as shown here. Notice that this expression is in some way analogous to the expression minus PdV we had for the work that occurs during a reversible transition in which only the volume of the system changed. In that expression, we were integrating over a change in an extensive thermodynamic variable, the volume, and the integrand was the conjugate intensive thermodynamic variable, the pressure. In this expression, the integrand is an intensive thermodynamic variable, the temperature, and we are integrating over an extensive thermodynamic variable, the entropy, which is conjugate to temperature. Let's now suppose that our transition is isothermal, i.e. the temperature is constant throughout. We can now take T outside the integral because it is a constant, which brings us to the final result shown here. Let's now substitute this value for Q into the expression shown with a green star beside it, at the top of the slide. The first term becomes T2 delta S2 over T2, and the factors of the T2 in the numerator and denominator cancel out. The second term becomes T1 delta S1 over T1, so the factors of T1 cancel out too. We are thus left with delta S2 minus delta S1 equals 0, as shown here. In other words, the total change in entropy in going round our Carnot cycle is equal to 0. The final result that we have arrived at here is correct, but we have used our mathematical nomenclature in a dubious way in deriving this expression. The problem here is with the integrals, so let's scrub those out. In fact, let's get rid of all the working other than the correct final expression. In place of this working, let's redraw our plane showing the entropy of the system against the extensive variable, the volume of the system against the extensive variable that has something to do with the transfer of heat. In fact, let's stop being coy about this extensive variable and let's call it what it is, entropy. The point we have to remember is that when we write an integral like the one I wrote that was taken over ds, we are looking at how something changes, in this case the amount of heat introduced to the system, as we move along a line something like this. Consequently, in what I wrote, which was an integral over ds, we are looking at how much heat would be absorbed as we move in a direction parallel to the entropy axis. Remember, though, that during the isothermal expansion and contraction stages in the Carnot cycle, the volume of the system is also changing. We have thus calculated how much heat is absorbed by the system as long as we move along a line something like this. A line that is most definitely not parallel to the y-axis, or entropy axis. Now, this doesn't actually matter for the Carnot engine, as the heat transferred from the bath to the engine is the same regardless of the way that I move. This is a consequence of the conservation of energy, which I will discuss in my next video. I'm just pointing out these mistakes, as these are the sort of things that are easy to do and are the sort of things that can get you into trouble when done in other places. This digression aside, the important thing that we have arrived at is the result in the bottom right-hand corner of the slide. Whenever we go around the closed loop that is at the heart of the Carnot engine, the total net change in the entropy of the gas inside this engine is 0. This is important because it means that the entropy of an equilibrated state is a property of that state and it does not depend on how the state was prepared. As a consequence, if we move from equilibrium state A to equilibrium state B, the total change in entropy is always given by the following equation. It does not depend on the way in which the transition was performed. This is hugely important because it makes the mathematics of classical thermodynamics straightforward. We can examine everything in classical thermodynamics using the theory of partial differential equations. This realization is, in fact, how we are able to justify the statements that I've used throughout these videos, where I've stated that the state of the system is characterized by the extensive variables, and that the action that the system will perform on the environment is characterized by the values of the intensive thermodynamic variables. To be totally clear, the state of a one-component, one-phase system is given by the values of the entropy and the volume of the system. And with that profound conclusion, I will finish and thank you for your attention.